What if everything you know about life is wrong? What if Earth, this blue marble we call home, was not the first oasis in our solar system? It sounds like the stuff of science fiction, the kind of idea you'd expect to find buried in a dog-eared paperback on some forgotten shelf, but this is not fiction. It's a question that scientists have been quietly pondering for decades, and one that has grown louder with every new discovery from Mars, Venus, and the icy moons at the edges of our system.
The idea is simple and yet staggering. Perhaps life, in some form, began not on Earth, but on another world nearby. Perhaps Mars or Venus once wore the crown of habitability long before our planet was ready for life. And perhaps, if you trace the story back far enough, you might find that we are not as original as we think. This isn't about little green men building cities in the clouds. It's about something more subtle, more fundamental. Could there have been an era when life, even in its simplest form, found a foothold on another planet? Could life have flickered into being elsewhere before Earth had oceans, before it had skies, before it had a name? Before we dive deep into this speculation, let's ground ourselves in the one thing we know. Earth wasn't always the perfect cradle for life. Far from it. In fact, for a large part of its early history, Earth was spectacularly hostile. Imagine a young planet spinning beneath a dimmer sun, battered by constant asteroid impacts, its surface a sea of molten rock and choking fumes. The air was not the sweet oxygen we take for granted today, but a toxic haze of carbon dioxide, ammonia, and methane. It was a world that could kill you in seconds, and yet life, somehow, eventually emerged here. But here's the twist. While Earth was struggling through its violent adolescence, what were the neighbors doing? What was happening on the other rocky worlds of our solar system, Venus, Mars, even Mercury, during those first few 100 million years? Were they too drowning in chaos? Or could one of them have found calm before the storm? Let's start with the basics. Life as we understand it needs three things: liquid water, a source of energy, and the right chemistry. For most of the 20th century, Earth was considered unique in providing all three. But as we've learned more about the planets around us, that assumption has begun to crack. Today, we know that Venus once had oceans, Mars too. At different times, both worlds may have been not just habitable, but positively inviting compared to early Earth. It's an unsettling thought, isn't it? We tend to picture our world as the chosen one, the lucky outlier in a cosmic lottery. But what if, in the early chapters of the solar system's story, Earth was just another contender, and not even the first to play host to life? Before we set sail across billions of years, I'd love to know where in our world you're tuning in from tonight, and what time is it in there? What's your sky like right now? Strange, isn't it? We're about to wander through alien oceans and vanished skies, yet here we are, sharing this single moment across time zones and continents. Wherever you are, I'm glad you've joined me on this journey. If questions like this, slow, vast, and filled with wonder, are your kind of questions, consider tapping like or subscribing. It helps this fragile little signal drift farther to find other curious minds out there in the dark. No pressure, of course. Just an invitation, like a meteor glinting in the night, hinting at something waiting beyond.
Now, before we go any further, it's worth clearing up a common misconception. When we talk about life on other planets, most people's minds leap straight to advanced beings, creatures with cities, technologies, perhaps even spacecraft. That's not what we're discussing here. This isn't about lost alien empires or crashed saucers in the desert. It's about something humbler, something microscopic, the first sparks of life, the kind of life you'd need a microscope or a time machine to see. Single-celled organisms, microbes. The kind of pioneers that don't need much beyond a puddle, a bit of warmth, and a pinch of chemistry. These are the architects of biology's foundations. On Earth, they built everything that came after. If such life ever appeared on Venus or Mars, even briefly, it would be one of the most profound discoveries in history, because it would mean we are not alone in origin, that life can begin more than once, that biology isn't a miracle, it's a tendency. But let's not get ahead of ourselves. How likely is it really that life could have formed on another planet before Earth was ready? To answer that, we need to roll back the clock, way back. Picture the solar system as it was 4.5 billion years ago. Forget the neat orbits and quiet skies of today. Instead, imagine a scene of chaos. A young sun blazing hotter than before, its light filtering through a haze of dust. The planets, not the serene spheres we see now, but raw, half-formed worlds spinning through a shooting gallery of debris. Asteroids slammed into planets on a daily basis. Comets streaked past, trailing icy vapor. Mountains rose and melted within centuries. Oceans, where they existed, boiled and vanished under the fury of impacts, only to return as steam condensed into endless rain. It was a time of violence and volatility, and perhaps of opportunity, because amid the chaos, conditions for life may have existed briefly, here and there, like sparks in the dark. In those early millennia, Venus and Mars were not the forbidding worlds we know today. They were, by all accounts, remarkably Earth-like. Venus may have had shallow seas beneath pale skies. Mars may have boasted rivers winding through valleys, lakes pooling in craters, even an ocean in its northern hemisphere. They had the ingredients for life, and they had them early. Which raises the question, did they get a head start? Could Venus or Mars have birthed life long before Earth had even settled down? And if they did, where is it now? That's the journey we're about to take. From the oceans of ancient Venus to the river valleys of Mars. From the mysterious theory of panspermia to the question no one can yet answer. What if we're not the first? Settle in. The past is about to get strange.
If you were to glance at Venus through a telescope tonight, you might mistake it for a gentle beacon glowing softly in the twilight sky. The ancients certainly did. To the Greeks, it was Aphrodite. To the Romans, Venus, goddess of beauty. But that beauty is a lie. Beneath its creamy clouds, Venus is hell. The hottest planet in the solar system, hotter even than Mercury, despite being nearly twice as far from the Sun. Its surface is an inferno of crushed rock and choking gases, where temperatures soar above 460 degrees Celsius, hot enough to melt lead, and pressures would flatten a submarine. But here's the secret most people don't know. Venus wasn't always a furnace. Once, long before Earth was green, before it had forests or continents, Venus may have been blue. For billions of years, astronomers assumed Venus was lifeless and barren, perhaps always so. The first spacecraft to peek beneath its clouds in the mid-20th century confirmed a landscape of lava plains and shattered mountains. But in recent decades, something unexpected has emerged from the data. Beneath that infernal atmosphere lies a story of lost oceans. Computer models, combined with surface geology and atmospheric clues, suggest that Venus may have once had shallow seas. Not puddles, not fleeting pools, but real, planet-wide oceans of liquid water. Oceans that may have endured for hundreds of millions of years, perhaps even billions. It's a staggering thought, because if those oceans existed, so did the possibility of life. To understand how this could be, we need to rewind the clock about 4 billion years to an era when the sun was younger and fainter. In those early days, Venus was not much different from Earth. Both worlds were similar in size, density, and composition. They likely formed with comparable amounts of water, delivered by comets, asteroids, and the primordial soup of the solar system. For a long time, Venus may have had a mild climate, thick clouds to shield it from the sun, and seas deep enough to cradle the chemistry of life. But something happened. Slowly, insidiously, Venus began to change. As the sun aged, it grew brighter, sending more heat to the inner planets. On Venus, that extra warmth tipped the balance. Water began to evaporate. More water vapor meant more greenhouse effect, trapping even more heat. It was a runaway feedback loop, a spiral that could not be stopped. The oceans boiled, the clouds thickened, not with rain, but with acid. Hydrogen, the lightest element, leaked into space, leaving behind carbon dioxide, and lots of it. In time, the seas were gone, the surface baked dry, and Venus became the hell we know today. This transformation was not quick. It may have taken hundreds of millions of years, perhaps more than 1 billion, which means there was a window, a vast stretch of time when Venus could have been calm, temperate, and blue. Long enough for chemistry to start playing its tricks, long enough for life in some primitive form to take root. If that happened, what would it have been like? Imagine a shallow Venusian sea under pale skies, its water rich with minerals and heat from volcanic vents. No continents, no land animals, just endless warm shallows and scattered volcanic islands. In those seas, the first molecules might have begun to assemble. Chains of carbon, loops of RNA, tiny self-replicating systems, not alive as we know it, but on the way. And if that story sounds familiar, it's because it's our story too. On Earth, similar chemistry gave rise to life. On Venus, it could have happened first. The thought is intoxicating. A planet now dead as stone may have once been alive. But if it was, where did that life go? The brutal truth is that Venus is not merely unfriendly to life now, it's actively murderous. Any organism stranded on its surface would be cooked, crushed, and dissolved in seconds. There are no fossils to find, no seashells buried in the sand. Whatever lived there, if anything did, left no obvious trace. And yet the mystery lingers. Because while Venus's surface is hell, its clouds are strange. About 50 kilometers above the ground, high in the atmosphere, conditions are surprisingly mild. The pressure there is close to that of Earth, and the temperature hovers around 30 degrees Celsius, almost pleasant. It's a layer of thick sulfuric acid clouds, true, but scientists have speculated that hardy microbes, if they evolved in the oceans and somehow adapted, might have found refuge there when the surface became uninhabitable. Could life still be clinging to that floating sanctuary today? It sounds outlandish, but recent observations have teased us with hints. In 2020, astronomers detected a chemical called phosphine in Venus's clouds, a molecule that, on Earth, is mostly associated with biology. The findings sparked a frenzy of debate. Was it life? Was it chemistry we didn't understand? The evidence remains inconclusive, and many scientists remain skeptical. But the fact that the question was even asked tells you something. The idea of life on Venus, past or present, is no longer science fiction. And if Venus did have life long before Earth did, then it raises an even bigger question. Did that life stay there? Or did it travel? Could fragments of ancient Venusian life have found a way to escape, hitch a ride on an asteroid, and seed another world, perhaps our own? That's a possibility we'll return to later, but first we need to visit another world, one even more famous in the search for life, a world that, for billions of years, may have been Earth's twin in every way that matters. Next stop, Mars.
Look up at the night sky, and you'll see Mars as a tiny amber pinprick, a lonely ember drifting in the dark. For most of human history, we've wondered what secrets it might hold. In the late 19th century, some astronomers even believed they could see canals etched across its surface, built by an advanced civilization trying desperately to survive a dying world. That vision has long since faded. When the first spacecraft arrived, they revealed a desert, a cold, airless wasteland. No cities, no canals, no life. And yet, Mars refuses to give up its mysteries. Because the planet we see today is not the planet it used to be. Beneath its rusty dust lies a story written in stone, and it's a story that changes everything we thought we knew about life in our solar system. Billions of years ago, Mars was not a frozen desert. It was blue. The evidence is overwhelming. Ancient riverbeds snake across its surface, dry as bone now, but once carved by flowing water. Vast deltas fan out from the mouths of vanished rivers. Minerals, locked in Martian rock, whisper of chemistry that can only happen in the presence of water. Craters that today gape empty, once brimmed with lakes. And in the northern hemisphere, there are signs of something even grander. An ocean, stretching across plains the size of Earth's Arctic. This isn't speculation, it's science, drawn from decades of orbiters, landers, and rovers that have mapped every dune and sampled every pebble. And those maps tell us one thing. Mars once had what life needs most: liquid water. Not for a moment, not in fleeting bursts, but for hundreds of millions of years, maybe longer. Now, water alone does not guarantee life, but combine it with what we know about early Mars: a thicker atmosphere, a magnetic field to shield it from radiation, volcanic activity to recycle heat and minerals, and you have a planet that sounds eerily familiar. For a time, Mars was not Earth's poor cousin, it was its twin. So, did life begin there? That question keeps scientists awake at night, because if life can arise wherever conditions allow, then Mars had a head start. Earth took hundreds of millions of years to stabilize after its birth. Asteroids bombarded its surface, oceans boiled and froze, but Mars, being smaller, it cooled faster. Its crust hardened sooner. Its first rivers may have flowed while Earth was still racked in steam and fire. If timing matters, and it almost certainly does, Mars could have been the first cradle of life in the solar system. Imagine standing on Mars 3.5 billion years ago. The air is thin but breathable with effort. The sky is not pink but blue, streaked with clouds. Rivers thread through valleys. Lakes shimmer in the sunlight. At dawn, frost glitters on the slopes of volcanoes, and in the north, an ocean laps against a rocky shore. It's not Earth, but it's close enough that you'd feel a pang of recognition. Now picture what might have been happening in those lakes and rivers.
tiny chains of molecules swirling in warm pools, learning to copy themselves. Primitive cells, tough and stubborn, feeding on minerals, clinging to rocks. On Earth, that chemistry would give rise to bacteria, and then to everything else. On Mars, if the same process began, it might have started long before Earth's seas were calm enough to try. And then it ended. Mars began to die, slowly, quietly, almost politely. First, its magnetic field faded. Without that invisible shield, the solar wind, a stream of charged particles from the sun, began to strip away the atmosphere. As the air thinned, the planet cooled. Water retreated underground, froze or boiled into space. Rivers dried, lakes vanished, the ocean ebbed away until only dust remained. And life, if it existed, faced a choice: adapt or perish. Could it have adapted? Some scientists think so. Microbes are resilient. On Earth they thrive in scalding vents, in acid lakes, beneath kilometers of ice. If Martian life existed, it might have retreated underground, into pockets of briny water insulated from the cold. Even now, radar scans hint at strange reflections beneath the ice cap at the planet's south pole, signals that some interpret as liquid reservoirs. If that's true, then something could still be alive down there, in the dark, waiting. But here's where the story gets truly wild. What if life didn't just cling to Mars? What if it escaped? When Mars was young, impacts from asteroids were common. Huge collisions blasted chunks of Martian rock into space, rocks that, over millions of years, rained down on Earth. We found them, real Martian meteorites, lying in Antarctica, in deserts, even in people's gardens. They are time capsules from a lost world, and some contain tiny structures that, under a microscope, look almost biological. The evidence is debated, fiercely, but the possibility is haunting. Because if microbes once lived inside those rocks, and if even a few survived the journey through space, then the first life on Earth might not have started here at all. It might have started on Mars. If that's true, then everything you know about life's origins changes. Earth becomes not the birthplace of biology, but its adoptive home. We, all of us, could be Martians in disguise. Outlandish? Perhaps. But the evidence grows stronger with every rover that trundles across the red sand. Perseverance, the latest explorer, is hunting for traces of ancient organics in a dry delta where rivers once flowed. One day, those samples will come back to Earth, and if they whisper of life, even the faintest echo, the question will shift from "did it happen" to "where else did it happen first?" And if Mars was one chapter in that story, what about the others? What about the icy moons of Jupiter and Saturn, hiding oceans beneath shells of ice? What about the cloud tops of Venus, still warm, still strange? What about worlds we haven't even considered yet? But before we leap to distant moons, we need to face a bigger question, one that ties Venus, Mars, and Earth together. Could life move from world to world? Could biology itself be a traveler, a hitchhiker across the void? That's where we're going next. Because if the answer is yes, then the story of life is far older, far stranger, and far more connected than we ever imagined.
If life arose on Mars before Earth, the story doesn't have to end there. It opens a door to an even bigger, stranger idea, that life doesn't stay put, that it can travel, not across oceans or continents, but across worlds, across the cold, empty gulf of space. This concept has a name: panspermia. It sounds exotic, but its meaning is simple: seeds everywhere. The theory suggests that life, or at least the ingredients for life, can spread from one planet to another. That life might be less like a tree rooted in one place and more like a drifting dandelion, sending out spores on the cosmic wind. On the face of it, panspermia seems absurd. Space is hostile, a vacuum, frozen, bathed in lethal radiation. Surely nothing as fragile as life could survive out there. And yet we know something remarkable. Some life on Earth already can. Take the humble tardigrade, for example, also known as the water bear. A tiny creature, no bigger than a grain of sand, with 8 stumpy legs and a face like something from a children's book. Cute, yes, but practically indestructible. Tardigrades can survive boiling water, crushing pressure, and even the emptiness of space. They can dry out completely, shutting down almost every biological process, and then reawaken decades later when water returns. In 2007, scientists sent them into orbit. They endured the vacuum, the cold, the radiation, and when they came back, some were still alive. If a creature like that can survive space, what about a microbe? Microbes are even tougher. We've found them thriving in nuclear reactors, buried kilometers underground, clinging to Antarctic ice, lurking in volcanic vents. Some can shrug off radiation doses that would kill a human instantly. So, if a rock big enough to shield them from the worst of space's hazards were blasted into orbit, those microbes could, in theory, survive the journey. And that brings us to Mars and Venus. Both worlds, in their violent youth, were struck by countless asteroids. Some of those impacts were catastrophic, flinging billions of tons of rock into the sky. A fraction of those fragments escaped gravity altogether and drifted into space. Some, we know for certain, came to Earth. We've held them in our hands, real Martian rocks that crossed millions of kilometers to land on our planet. If dead rock can make the journey, why not living cargo? Picture it. An asteroid slams into a shallow Martian sea, vaporizing water, sending shockwaves through the crust. Chunks of crust that may harbor tiny, tenacious microbes, are hurled into the heavens. They tumble through the void for millennia, spinning silently, baked by sunlight on one side, frozen on the other. Inside, shielded from radiation, in microscopic cracks, life sleeps. Until one day, gravity draws that rock into Earth's atmosphere. It blazes briefly, but the interior remains cool. The rock falls to the ground. Rain seeps in. Warmth returns. And something stirs. Science fiction? Perhaps, but the physics is sound. We've simulated the shocks, the temperatures, the trajectories. We've even found Martian meteorites on Earth. One of them, ALH 840001, discovered in Antarctica, sparked global headlines in the 1990s because it contained tiny shapes that looked like fossil microbes. The claim remains controversial, but it reminds us that the idea of life hitchhiking across planets is not beyond imagination. In fact, it may have happened more than once. Some scientists believe this traffic of rocks between Mars and Earth was constant during the early solar system. Thousands of fragments might have landed here, and some may be still arriving today. If even one carried viable microbes, then Earth's first life might not have started in a warm pond or a hydrothermal vent. It might have started on Mars, or Venus, or somewhere else entirely. And here's where things get dizzying. If life can leap from planet to planet, then the story of life is not local, it's interplanetary, even interstellar. Because panspermia doesn't have to stop at our solar system. When stars are born close together, as ours once was in its stellar nursery, the distances between them are tiny compared to the empty space of today. In those crowded nurseries, debris from planetary collisions could drift from one star system to another. Slowly, yes, over millions of years, but not impossibly. If microbes can sleep for eons, then the seeds of life might travel across the galaxy like spores on a breeze. Which raises a breathtaking possibility. Life might not be a miracle unique to Earth. It might be common, a pattern, a tendency. And if that's true, then our origins are tangled with worlds we've never seen. We might share a family tree with organisms beneath the ice of Europa, or with microbes drifting in Titan's methane haze. But before we leap to other stars, let's stay closer to home. Because if panspermia can happen, it could work both ways. If life began on Mars and came to Earth, some of it might have stayed behind. If life began on Earth and later fragments of rock were blasted into space by an asteroid impact, some of those fragments might have landed on Mars or Venus, which means even if those planets are lifeless now, they could hold fossils of Earth life, time capsules from a younger world. The idea is humbling, even unsettling. We picture life as rooted, fixed, belonging to its planet. But maybe life is a wanderer, a traveler, a hitchhiker in the void. And if that's true, then the story of biology is not just Earth's story, it's the solar system's story. Next, we'll look at how this journey of life, if it happened, fits into a bigger pattern, the strange dance of habitability that shaped Venus, Earth, and Mars. Why did two of them fall, while one survived? And could the same fate await us?
Once upon a time, the inner solar system was home to three sisters. Three rocky planets orbiting the Sun, each warm enough to hold liquid water, each kissed by starlight and crowned with clouds. Venus, Earth, and Mars. For a brief span, a cosmic heartbeat, they may all have been habitable together. Oceans lapping on their shores, rain falling from their skies, chemistry bubbling in their depths. And yet, look at them now. One is a frozen desert, another a crushing furnace. Only Earth remains green and blue, its seas alive with billions of beating hearts. Why? The answer lies in a delicate balance. A balance so fragile that the smallest shift can tip a world from paradise into oblivion. Let's start with Venus, the elder sister. Similar in size to Earth, forged from the same primordial dust, it began with every advantage. Its gravity was strong enough to hold an atmosphere. Its surface likely boasted shallow seas, scattered islands, perhaps even continents. But Venus lived too close to the Sun, just 40 million kilometers closer than Earth, but that made all the difference. As the young Sun brightened over billions of years, Venus absorbed more heat. Its oceans began to simmer, then steam, releasing water vapor, a greenhouse gas far more potent than carbon dioxide. That vapor trapped more heat, which drove more evaporation, which trapped more heat still. A runaway spiral. The seas boiled away. Without oceans to absorb carbon, volcanic eruptions pumped greenhouse gases into the air unchecked. The planet became a pressure cooker,
90 times Earth's atmospheric weight pressing down on a scorched surface. Temperatures soared beyond 460 degrees Celsius. Whatever life might have flickered there was extinguished, erased without trace. Mars, the youngest sister, suffered the opposite fate. It lived farther from the sun, in a colder neighborhood, but in its youth it too was warm enough for rivers and lakes. The evidence is carved into its valleys and written in its minerals. For perhaps 500 million years it was a world of water. But Mars had a fatal flaw. It was small, barely half Earth's size, with weaker gravity and a feeble magnetic field. That magnetic field, powered by a churning molten core, was Mars's shield, its armor against the solar wind, the torrent of charged particles streaming from the sun. When the core cooled and the field faded, that armor shattered. The solar wind began stripping the atmosphere away, molecule by molecule. As the air thinned, pressure dropped. Liquid water, once stable, began to boil and vanish into space. The surface froze, the rivers died, the oceans retreated into ice and rock. And so Mars, like Venus, fell. One drowned in heat, the other suffocated in cold. Which leaves Earth, the middle sister, balanced on the knife edge of habitability. Why did Earth survive when her siblings perished? Partly it's luck. Earth orbits in the so-called habitable zone, the Goldilocks belt, where liquid water can persist, not too close to the sun, not too far. But luck alone is not enough. Earth also had geology on its side. Unlike Mars, Earth was big enough to keep its core molten, generating a magnetic field that shields us to this day. That same internal heat drives plate tectonics, the restless dance of continents that recycles carbon between the crust and the atmosphere, stabilizing the climate over eons. And unlike Venus, Earth had just the right amount of water. Not so much that it drowned its own carbon cycle, not so little that it dried out. Even so, Earth's history has not been a smooth ride. There were times when it teetered on the edge, times when ice smothered the planet from pole to pole, times when volcanoes spewed poison into the skies, times when asteroids turned day to night. But through it all, Earth recovered. Venus and Mars did not. And here is the sobering truth. Earth's good fortune is not guaranteed forever. Our magnetic field is slowly weakening. The sun is still brightening. In 1 billion years or so, Earth may follow Venus into the furnace. That is the ultimate fate of all worlds orbiting stars like ours. Habitability is temporary. But in the meantime, we have this brief window, this shimmering interlude of stability in which to ask questions. And the question before us now is this. If all three sisters were once habitable, could they have shared more than conditions? Could they have shared life? Could biology have leapt from Venus to Earth or from Mars to Earth in those early days of chaos? If the answer is yes, then our family tree does not grow from a single root, but from a braided river of origins, worlds swapping seeds like wildflowers in the wind. In the next chapter, we'll explore what happened after those early days of chaos faded. How did Earth, the survivor, go from molten rock and acid rain to a cradle of life? And how does that journey compare to the fates of Venus and Mars? Because in understanding that, we might glimpse the truth of whether life began here or merely arrived.
If you could travel back in time to the moment Earth was born, you would not recognize it.
Forget blue skies and green forests. Forget oceans glittering in sunlight. What you'd find instead is chaos, raw, molten chaos. A world still glowing from its own formation, its surface a restless sea of magma, its skies thick with choking fumes. 4.5 billion years ago, Earth was hell, literally. The geologists called this time the Hadean Eon, after Hades, god of the underworld. The name fits. Volcanoes tore through the crust in endless fury. Asteroids rained down like artillery, some so large they boiled entire oceans to steam in an instant. The moon itself was born from one such cataclysm, a collision between the young Earth and a planet-sized body, shattering both worlds and leaving behind a disk of molten debris that coalesced into the pale companion we see today. It was a world that should have been hostile to life, and for hundreds of millions of years it was. Oceans, when they formed, were blasted away by impacts. The surface simmered beneath a dense, poisonous atmosphere. Lightning split the skies. No plant, no animal, no microbe could have endured it. And yet, something did. Somewhere, somehow, life began. The question is, how? And why here, when Venus and Mars seemed just as promising in those early days? The answer lies in timing. After the violence of Earth's birth, there came a lull, a precious window when conditions softened just enough for chemistry to weave its magic. Oceans formed and stayed. The air thinned and cooled. Volcanoes still rumbled, but their fury eased. In this calmer interlude, Earth had what life needs most: stability. Not forever, not even for long, but long enough. In pools and seas warmed by the young sun, molecules danced. Carbon, hydrogen, nitrogen, the building blocks of biology collided and combined in countless variations. Most combinations fell apart. A few endured. Some formed chains that could copy themselves, crude ancestors of DNA and RNA. Those chains learned to hide inside tiny bubbles of fat, the first cell membranes, and from those fragile beginnings came the first true organisms, single-celled, simple, and utterly revolutionary. It is a story we piece together from clues, from ancient rocks in Greenland and Australia, from chemical signatures in crystals older than mountains. The oldest fossils we've found date back 3.5 billion years, but the chemistry of life may reach deeper still, into a time when Earth was barely out of its adolescence. If you could stand on Earth then and somehow survive the sulfuric air and crimson skies, you would see no forests, no flowers, no fish, just bare rock, steaming vents, and shallow seas tinted green with colonies of microbes. But those microbes were doing something extraordinary. They were eating, they were growing, they were dividing. They were, in their blind, relentless way, transforming the planet. Over hundreds of millions of years, those tiny cells became the architects of Earth's habitability. They filled the oceans, forming mats and reefs. They learned to harvest energy from sunlight, exhaling oxygen as waste, a waste that would one day become the breath of animals. They were shaping the future, atom by atom, unaware that they were laying the foundations for forests and whales and humans. And yet, even as life bloomed here, the other two sisters fell silent. Venus boiled. Mars froze. Their oceans vanished, their skies collapsed. Earth was left alone to bear the torch. But was it truly alone in origin, or had life already tried its luck elsewhere? That question haunts every fossil we unearth, every experiment we run in laboratories, every signal we scan from the stars. Because the chemistry that sparked life here is not unique to Earth. It is written into the laws of physics, stitched into the fabric of the cosmos. Wherever water flows, wherever energy pulses, wherever molecules can meet, life seems possible, perhaps inevitable. And so we circle back to the question at the heart of this journey. If Earth could do it, why not Venus? Why not Mars? Why not both? Could life have flickered on those worlds before Earth was ready? Could it have started in their oceans, thrived for a while, then perished when fate turned cruel? Or could it still linger, hidden in a Martian cavern or drifting in the clouds of Venus? Science cannot answer yet. But every rover that crawls across the red sands, every probe that peers through Venus's haze, brings us closer. And if we ever find proof, even a single microbe that is not of this Earth, it will rewrite our understanding of biology, of evolution, of ourselves. But let's stay in the deep past for a little longer, because Earth's story is not just about how life began, but how it endured. Our planet has faced extinction more than once, and at each time, life adapted, changed, and continued. That resilience is part of the reason we're here, and it might also explain why life, if it arose on other worlds, could survive in places we'd least expect. In the next chapter, we'll travel beyond Earth, not forward in time, but sideways in imagination, to picture what ancient Venus and Mars might have truly looked like. Worlds alive, worlds with skies and seas, worlds that could have been our first home.
Close your eyes for a moment. Forget the Venus and Mars you know, the hell planet and the frozen desert. Erase the images of sulfuric skies and rusty dust. Instead, let's wind the clock back billions of years to an era when these worlds were not dead, when they might have been beautiful. Picture Venus first. The Sun is younger, dimmer. Venus orbits slightly closer than Earth, but for now, the heat is gentle. Its clouds are soft and white, not the suffocating shroud they wear today. Beneath them lies an ocean, shallow, warm, stretching across lowlands like a silver mirror. Waves lap against volcanic islands, green with primitive life. The air is thick, but not unbearable, a humid greenhouse rich in carbon dioxide and nitrogen, perhaps with wisps of water vapor swirling under a pale sky. The seas ripple with chemistry. Perhaps they teem with microscopic cells, drifting lazily in sunlit shallows, harvesting energy from minerals or from the faint light filtering through the clouds. No forests, no flowers, no fish, only simple life, unhurried, unaware that its paradise is temporary. For 1 billion years, maybe more, Venus might have known this peace. Rain fell, rivers ran, winds carried clouds across a gentle horizon. And then, almost imperceptibly, the change began. A little more heat from the sun, a little more evaporation. Clouds thickened, trapping warmth. The seas began to shrink. The greenhouse spiral tightened. Slowly, Venus's blue face turned grey, then gold, then hellish red. Its ocean boiled, its sky became acid, and whatever lived there, if anything lived at all, was gone. Now turn your gaze outward, past Earth, to Mars. Today it is a world of rust and silence. But long ago, it may have been a world of rivers and rain. Imagine standing on an ancient Martian plain.
The air is thin by Earth standards, but thick enough to carry clouds across the sky. That sky is blue, not the pink haze we know now, but a soft, faded azure. Before you stretches a winding river, carving its way through valleys etched by water over millions of years. Beyond lies a lake, shimmering under a cold sun. Perhaps in the far north, an ocean curls around a continent-sized basin, its waves licking at stony shores. Volcanoes loom in the distance, titans like Olympus Mons, already stirring, their slopes cloaked in frost. Mars was colder than Earth, but not frozen. Greenhouse gases kept its climate mild enough for liquid water to persist. Hydrothermal vents bubbled in its depths, and in those waters, chemistry might have danced the same dance it did on Earth, molecules forming chains, chains folding into loops, loops learning to copy themselves. The first spark of life, perhaps flickering in a Martian tide pool. For hundreds of millions of years, Mars may have thrived like this, long enough for life to begin and maybe even flourish in simple forms. But fate was cruel. The planet's heart cooled, its magnetic field withered, the solar wind stripped away its air, the lakes dried, the rivers cracked into empty beds, the ocean vanished into frost and stone. Mars became what we see today, a desert haunted by the memory of water. And yet, what if that memory is more than stone? What if even now in some hidden crevice deep underground something still lives? A colony of microbes huddled in a briny pocket, asleep but not dead, waiting for warmth that may never come. When we imagine these ancient worlds, we are not indulging in fantasy. We are building on evidence. Rivers etched into rock, minerals forged in water, isotopes locked in ancient sediments. Everything we know says that Venus and Mars were once habitable. The only missing piece is proof that life took advantage of that opportunity. If it did, those worlds were not just neighbors, they were rivals. For a fleeting age, 3 planets may have shared one destiny, to become alive, but only one succeeded. Or did it? Perhaps Venus bloomed first, then perished, its biology erased by fire. Perhaps Mars stirred next, then froze, leaving fossils in its icy bones. Perhaps Earth, late to the party, inherited what its sisters lost, seeds flung across space by impact and time. And perhaps those seeds are still out there, waiting for us to find them. In the next part, we'll look at the tantalizing evidence that could answer this question. Not speculation, but science. Hard data from probes, rovers, and telescopes that hint at ancient oceans, strange chemistry, and just maybe, life. Because imagination can take us only so far. To go further, we need proof.
Speculation is powerful, but science demands evidence. If Venus and Mars were once alive, there should be traces, whispers in the dust, clues in the rock. And for decades, we've been listening, searching, digging. What have we found? Let's start with Mars, because the red planet has been generous with its secrets. Every rover we've sent there, from Sojourner to Spirit and Opportunity, from Curiosity to Perseverance, has told us the same thing. Water was here. Not briefly, not in passing, but for long ages.
We've seen river valleys carved into the highlands, winding for hundreds of kilometers. We've found deltas frozen in time, fans of sediment spreading from the mouths of vanished rivers into what were once lakes. We've detected minerals that only form in water, clays, sulfates, carbonates. And we've found layered rocks that speak of sediments settling quietly, year after year, under a still surface. At Gale Crater, curiosity drilled into ancient mudstone and found organics, carbon-based molecules, the raw ingredients of life. They weren't fossils, not proof of biology, but their presence was a revelation. They showed that Mars had what life needs: water, chemistry, energy. Perseverance has gone further. It's exploring Jezero Crater, a dried-up lakebed where a river once flowed. There, it has sampled rocks that were once in contact with water, and it will cache those samples for return to Earth. One day, perhaps a decade from now, they will arrive in laboratories where scientists can probe them atom by atom, searching for signs of ancient life. If even a single microfossil turns up, the question will no longer be, did life arise twice in one solar system? It will be, how common is life in the universe? But Venus isn't the only world whispering to us. Venus, though harder to reach, has raised its own questions. For years, scientists believed Venus had nothing left to say. Its surface is hell, and its thick clouds make observation a challenge. But then came 2020. A team announced the detection of phosphine in the planet's clouds, a gas that, on Earth, is mostly produced by life. The finding was controversial. Some scientists questioned the data. Others argued for non-biological explanations. Later observations have cast doubt on the signal. And yet, the debate changed something fundamental. It reminded us that Venus cannot be written off. Its clouds, 50 kilometers above the surface, are harsh, but not impossible for microbes. Warm, temperate, shielded from the worst heat below. Could something be lingering there, drifting on droplets of acid, clinging to existence as its world burns beneath? We don't know, but we are looking. Future missions like NASA's Veritas and Da Vinci Plus and ESA's Envision will probe Venus with new eyes, mapping its surface, sampling its air, searching for signs that this planet once knew water and maybe life. Even closer to home, in laboratories on Earth, the search continues. We've studied Martian meteorites, real pieces of the red planet flung to Earth by ancient impacts. One, ALH 84001, found in Antarctica, became famous in 1996 when scientists reported microscopic structures inside it that looked like fossil bacteria. The claim ignited headlines, political speeches, and a storm of debate. Today, most experts think those shapes were non-biological, formed by chemistry. But the meteorite still matters. It proved that Mars rocks can travel here, and if rocks can make the journey, so could life. All these clues, dried rivers, ancient minerals, organic molecules, possible biosignatures, don't prove life, not yet. But they tell us something profound. The conditions for life were there. Not for minutes, not for moments, but for ages long enough for chemistry to dream. And that brings us back to the question at the heart of this story. If life didn't start on Mars or Venus, why not? Was there some missing ingredient, some fatal flaw that stopped biology in its tracks? Or did it start and then vanish, leaving only traces we haven't learned to read. Science is patient. It will take decades, maybe longer, to know for certain, but while we wait for answers from dusty craters and acid clouds, there's another path to follow. Not the search for fossils or molecules, but the study of possibility itself. In the next part, we'll explore what scientists are doing here on Earth, in labs and experiments, to understand how life begins. And we'll ask a question that reaches beyond planets, beyond stars. Is life a fluke or a law? Does it arise only once in a trillion tries, or is it the universe's default setting? Because the answer to that shapes everything. Not just our past, but our future.
If life arose on Venus or Mars, it had to start somewhere, with chemistry. But how does chemistry become biology? How do blind molecules organize themselves into something that eats, grows, and replicates? That question has haunted science for centuries, and the answer might be the key to understanding whether life could have appeared not just here, but there. To tackle it, scientists have tried to recreate the first steps of life in the laboratory. The most famous attempt happened in 1953, when two researchers, Stanley Miller and Harold Urey, built an experiment that changed everything. They sealed a mixture of gases, methane, ammonia, hydrogen, and water vapor, inside a glass chamber meant to mimic the atmosphere of early Earth. Then they sparked it with electricity, simulating lightning. Within a week, the liquid inside turned pink, then brown. When they analyzed it, they found amino acids, the building blocks of proteins, the raw material of life. It was a stunning result. From simple gases and a little energy, the molecules of biology had emerged. Not life itself, but its ingredients. The experiment proved that life's chemistry is not magic. It's physics and chemistry, obeying natural laws. And if those laws operate here, they operate everywhere. Since then, the story has grown richer. We've learned that amino acids can form not just in lab flasks, but in space, in the icy hearts of comets, in the dark between stars. Meteorites that have fallen to Earth contain not only amino acids, but sugars, even the bases of RNA. The universe, it seems, is littered with life's Lego bricks. But bricks aren't enough. To build life, you need structure. Molecules that copy themselves, pass on information, evolve. One leading theory is the RNA world. RNA is a cousin of DNA, capable of storing genetic code, but also of acting like an enzyme, speeding up reactions. In experiments, scientists have coaxed RNA strands to copy themselves, clumsily, imperfectly, but enough to hint at how the first replicators might have worked. Another theory points to hydrothermal vents, deep-sea chimneys where superheated water, rich in minerals, gushes into the ocean. These vents create natural gradients of heat and chemistry, ideal for powering reactions. On Earth, life thrives around such vents, even today. Could similar vents have existed in the seas of Venus or Mars? Almost certainly. And then there's clay, humble, ordinary clay. In the lab, it can act like a scaffold, encouraging molecules to assemble into chains. Early Earth was covered in clay-rich sediments. So were early Mars and, likely, early Venus.
Wherever you have water and rock, you have clay. All these findings suggest something profound. Life may not need a miracle. It may only need time, water, and a little energy. Given those, chemistry seems determined to grow more complex. If that's true, then the question shifts. Not could life arise on Venus or Mars, but how could it not? Both worlds had the ingredients. Both had energy, sunlight, volcanoes, maybe even lightning. Both had water for millions of years. On Earth, that was enough. Why not there? Perhaps it was enough. Perhaps life began on those worlds, tiny and tentative, only to vanish when conditions changed. Or perhaps it survived, clinging to a shadowy refuge, deep beneath the Martian crust, high in the clouds of Venus. To find out, we must keep searching. But while probes and rovers hunt for fossils, scientists here on Earth are also looking outward, beyond our solar system, to worlds orbiting distant stars. And what they're finding suggests that habitable planets might not be rare jewels, but common stones. In the next part, we'll leave the solar system behind for a moment to glimpse the wider stage. Thousands of exoplanets have been discovered, many of them rocky, many in their star's habitable zone. If Earth wasn't first in our system, could there be thousands of other firsts across the galaxy? And if life can spread between planets, could it spread between stars? Because if the universe is generous with planets, it might also be generous with life. And that possibility changes everything. So far, we've wandered only among familiar shores: Venus, Earth, Mars. Three sisters in the sun's embrace, sharing one fragile strip of habitability. But what if that strip is not unique? What if there are other shores, other oceans, scattered across the galaxy? Once, this was speculation. Today, it's science. We've found them, thousands of them. The first exoplanet, a planet orbiting another star, was confirmed in 1992. Since then, our telescopes have swept the sky, and what they've revealed is astonishing. Planets are everywhere. Almost every star you see at night likely has at least one. Some have dozens. The Milky Way may hold 100 billion planets, and among them, billions of rocky worlds, not so different from our own. Of those, many orbit in the so-called habitable zone, the Goldilocks region where liquid water could exist. Some circle small red dwarfs, glowing like embers. Others dance around suns like ours. We found super-Earths, planets larger than ours but still rocky, and mini-Neptunes swathed in clouds. We've even glimpsed worlds that might have oceans, clouds, weather. The numbers alone are dizzying. If even a fraction of these planets are truly habitable, then life should not be a miracle. It should be a pattern. But here's where the question deepens. If life is common, is it also connected? Does panspermia, the cosmic hitchhiker, leap not just between planets, but between stars? Some scientists think so. In the crowded nurseries where stars are born, the distances between them are small, a few light years, sometimes less. In those early times, debris from collisions could drift from one system to another. It would take millions of years, but time is the one thing the universe has in abundance. And if microbes can endure for millennia in the dark, sheltered inside rocks, then perhaps the seeds of life could scatter across entire clusters of stars, like spores riding a galactic wind. If that's true, then life may not only be widespread, it may also be related. The chemistry that stirred on Venus or Mars could echo on planets circling alien suns. Perhaps life everywhere shares the same root, not because of chance, but because it all began with the same drifting dust, the same ancient spark. But yet for all these worlds, all these possibilities, we still have only one confirmed example: Earth. That is both humbling and thrilling. Because if we find even one more, just one, the implications will be vast. 2 origins in one galaxy would mean the universe teems with life. 2 origins in one solar system would mean it practically bursts with it. And that's why Mars and Venus matter so much. They are the test case, the experiment running in our own backyard. If we find life there, even fossil life, even dead life, it will tell us that biology is not a fluke, it is a force. But before we race too far into the stars, let's return to our theme. What if Earth wasn't the first? What if life began on Mars or Venus and then came here? What would that mean for us, for our identity, for the way we see ourselves in the cosmos? In the next part, we'll turn to that question. We'll explore the theory that Earth is not the cradle of life, but its refuge. That we, every tree, every bird, every person, might carry an inheritance from a lost world. And we'll ask, if that's true, how could we ever know? Because proof, if it comes, will not just change science, it will change the story of who we are.
We like to think of Earth as the origin of all things living, the cradle where life first opened its eyes. But what if that's a comforting illusion? What if Earth was never the cradle, only the refuge? It's a possibility that unsettles some and thrills others. Because if it's true, then our story is not purely Earth's story. It began on another world, and that world is gone. The idea rests on 3 pillars: timing, transfer, and survival. Let's take them one by one. First, timing. Earth was born in fire. For its first few 100 million years, it was hammered by asteroids in what scientists call the Late Heavy Bombardment. Oceans boiled, crust melted. Any fragile molecules trying to form life would have been obliterated again and again. Venus and Mars, smaller and quicker to cool, may have had calm seas, while Earth was still chaos. If timing matters, and it surely does, then those worlds had a head start. Second, transfer. We know rocks travel between planets. We found Martian meteorites on Earth, real pieces of Mars hurled into space by impacts, drifting for millions of years before falling here. Some impacts were so violent that they could fling tons of debris into interplanetary orbits. If life existed on Mars or Venus when those impacts struck, fragments of their crust might have carried microscopic hitchhikers. Shielded inside rock, microbes could sleep through the cold, the radiation, the long, dark journey. In 2019, scientists revived microbes from permafrost that had been frozen for tens of thousands of years. A few hardy spores deep in rock might last for millions. If all 3 pillars stand,
If another world had life, if rocks carried it here, if that life endured, then Earth's first organisms were immigrants. We are, quite literally, aliens to our own planet. What would that mean? For biology, it would be seismic. It would tell us that life is not rare, that it leaps between worlds whenever it can, like a traveler catching the next passing ship. For philosophy, it would be profound. It would make us children not of Earth alone, but of the solar system. Our roots would wind back through space, through eons, to a lost ocean on a distant world. And here's the strangest part. We may never know for certain. If life on Mars or Venus started and then seeded Earth, its descendants would have evolved beyond recognition. Billions of years of mutation and adaptation would have erased every trace of their alien origin. Unless we find life that stayed behind. That's why the search for fossils on Mars matters so much. That's why the hint of phosphine in Venus's clouds caused such a stir. If we discover organisms on those worlds that use the same genetic code as ours, the same DNA, the same amino acids, then we'll know we're family. We'll know life is not an accident, but a contagion, spreading wherever it can. But if we find something truly alien, something built on a different chemistry, then the story changes again. Two origins in one solar system would mean life arises easily, inevitably, whenever conditions allow. And that would make the universe a garden. For now we live in the in-between. We dream, we speculate, we send machines to scrape dust and drill rock, hoping for a sign. One fossil, one cell, one whisper from another time. But while we wait, let's ask a different question. Not where life began, but where it could go. Because if life can move from world to world, what happens when a world dies? Does life end with it, or does it flee, looking for a new home? That question is not theoretical, it's our future. One day Earth too will fall, to heat, to cold, to time. And when it does, will life go quietly, or will it take to the stars? In the next part, we'll explore that idea. The possibility that life is not a victim of worlds, but their conqueror. That biology is not tied to planets at all, but destined to roam.
When a planet dies, does life die with it? Or does it fight, cling, and search for a way out? It's easy to think of life as bound to its world, like a tree rooted in soil. But what if life is not a tree at all, but a traveler? What if survival, not attachment, is its deepest law? On Earth, we've seen life endure every catastrophe the cosmos has thrown at it. Asteroid strikes that turn skies to fire, ice ages that smothered continents, supervolcanoes, poisons and plagues. Time and again, life has bent without breaking. It adapts, mutates, hides in cracks and caves. Some microbes can survive boiling water. Others cling to ice at -80 degrees. There are organisms that feast on radiation, that thrive without sunlight, that outlast vacuum itself. So what happens when an entire planet becomes uninhabitable? We know Venus faced that fate. A runaway greenhouse turned its oceans into steam, its skies into acid. If life had taken hold there, it had only two options:
Evolve to endure the clouds, or vanish? Perhaps it tried. Perhaps, high in the temperate layers of Venus's atmosphere, tiny survivors still drift, cocooned in droplets. Mars faced the opposite doom. Its core cooled, its shield faded, its air blew away. Its rivers froze into stone. If life lived there, perhaps it burrowed underground, clinging to warmth deep in the crust. We can't rule that out, not yet. But if those havens failed, what then? Could life leave its home behind? Could it ride the violence of an asteroid strike, sealed inside a splinter of rock, and drift into the void? We know the physics works. Impacts can fling debris into space at escape velocity. We know the journey is survivable. Microbes have endured years on the exterior of the International Space Station, exposed to vacuum and radiation. Shield them inside stone, and they might last millions of years. This idea that life migrates is called lithopanspermia. It may sound like science fiction, but it is rooted in hard data. Martian meteorites lie on Earth today, proof that rocks travel between planets. And inside those rocks, we've found structures and minerals that just hint at biology. If life can escape one world, then no planet is an island. Biology becomes a web, threads of living matter stretched between worlds. A planet dies, but its life endures, hitchhiking to the next refuge. Perhaps Earth was that refuge once. Perhaps it will be again. And here's the thought that should make you pause. One day, Earth will need the same escape route. Our sun is brightening. In 1 billion years, oceans will boil, skies will burn. If humanity still exists, we will flee with rockets and ships. But what about the rest of life? The bacteria, the spores, the silent majority that built this world? Perhaps they won't need ships. Perhaps they'll do what they've always done: cling, endure, and wait for chance. An asteroid strike could blast fragments of Earth into space. Some will fall on Mars, others on the moons of Jupiter. Perhaps a few will drift far beyond, out of the solar system, toward stars unborn. Life will not ask permission, it will simply go. This vision reshapes everything we think we know about biology. Life is not fragile, it is ferocious. It does not accept extinction. It moves, it persists, it rewrites its own story in the dust of worlds. And if that is true, then the cosmos may be littered not just with planets, but with fossils of travelers, ancient spores adrift in the dark, fragments of DNA frozen in comets, seeds waiting for a home. If life wanders, then Earth is not the first port, and it will not be the last. We are one chapter in a saga written across the stars. But before we drift too far into the future, let's return to the evidence and to the question that started all this. Could life have migrated into Earth long ago, from Venus or Mars? And if so, could we ever prove it? In the next part, we'll explore that mystery and the cutting-edge research trying to find traces of our alien ancestry. Because if Earth wasn't the first, the proof might already lie
beneath our feet.
If life began on Mars or Venus and later came to Earth, it would be the greatest revelation in the history of biology. But how could we ever know? After billions of years of evolution, would any trace of that alien origin remain? At first glance, the answer seems hopeless. Life changes. It adapts, mutates, transforms. A microbe that arrived on Earth 4 billion years ago would be unrecognizable today. Its descendants would have diverged beyond comparison. Fossils from that time are scarce, even on Earth. On another planet, they would be harder still. And yet, the quest is not impossible. One path lies in genetics. All life on Earth shares a common code, the language of DNA, written in 4 letters, A, T, C, G. We also share the same 20 amino acids, the same handedness in molecules. If we found life elsewhere using the same alphabet, it would raise 2 possibilities. Either life is constrained to one chemistry everywhere, or it shares a common ancestor. If Martian microbes use different amino acids, different chirality, or an entirely different genetic system, then we would know life arose twice independently in one solar system. That would be staggering. But if it uses the same system as us, then the case for a shared origin grows strong. Another path lies in isotopes, the subtle fingerprints of elements. On Earth, life prefers lighter isotopes of carbon and nitrogen, leaving distinctive ratios in rocks. If we find the same patterns on Mars, it could signal biology. If those patterns match Earth's in unexpected ways, it might hint at kinship. Then there is fossil evidence. Mars, unlike Earth, lacks plate tectonics. Its surface is ancient, frozen in time. Craters and deltas have lain undisturbed for billions of years. If life ever lived there, its traces might still linger in layered sediments or in the pores of rocks. That's why NASA's Perseverance rover is drilling cores from Jezero Crater, an ancient lake bed, and caching them for return to Earth. Those samples could hold microfossils, chemical signatures, or even preserved organics. Venus is trickier. Its surface has been resurfaced by volcanoes, burying any record of its early history. But its clouds remain a mystery. If we sent probes to skim those clouds, to sniff their chemistry and search for cells, we might find the last refugees of a once blue world. And then there is a more radical idea. Find life on Earth that doesn't belong here. A shadow biosphere, organisms so different from known life that we've overlooked them. If such life exists, it could be a relic of a separate origin, perhaps seeded from another planet. Scientists have searched, without success so far, but the possibility lingers. If we ever confirm that Earth life is not unique, that it shares roots with life beyond, the implications are profound. It would mean biology is not a miracle confined to one blue dot, but a cosmic force, an inevitable outcome of physics and chemistry. It would also mean that life spreads, that it does not respect planetary borders, that it leaps whenever it can. And if that's true, then the question, are we alone, becomes almost absurd. If life began more than once in one solar system, it must bloom on countless worlds across the galaxy. It may be everywhere, under ice shells, in methane lakes, on worlds orbiting red suns. But let's not rush ahead. For now, the evidence is incomplete. We have hints, whispers, shadows in the dust. No fossils, no cells, no unambiguous proof. Not yet. And so we wait for the samples from Mars, for the probes to Venus, for the next generation of telescopes to peer into alien skies. One day, perhaps soon, the answer will come. Until then, the question remains and grows stranger the more we ask it. Because if life moves between worlds, if Earth was not first, then what of other planets, moons with oceans, comets rich in organics, asteroids carrying frozen seeds? How far does the web of life stretch? In the next part, we'll journey outward, beyond Mars, beyond Venus, to the icy moons that may hold vast hidden seas. Worlds like Europa and Enceladus, where life could still thrive in darkness. If Earth wasn't the first, these worlds might be the next.
So far, we've lingered close to home. Venus, Earth, Mars. Three sisters, once perhaps united by oceans and clouds. But the solar system holds other secrets, far from the warmth of the sun. Worlds so cold they seem dead, yet beneath their frozen faces they may hide something extraordinary. Oceans. Take Europa, one of Jupiter's 4 great moons. On the surface, it is a cracked white desert of ice, crisscrossed with scars where the crust has split and healed. It looks inert, lifeless. But listen closely to the whispers from our spacecraft, and a different picture emerges. Beneath that icy shell, perhaps 20 kilometers thick, lies an ocean, a global ocean deeper than all Earth's seas combined, locked in darkness, warmed not by sunlight but by heat from the moon's interior, stirred by tidal forces as Jupiter's gravity kneads it like dough. Water, energy, time, the holy trinity of habitability. And Europa is not alone. Enceladus, a tiny moon of Saturn, hides a similar ocean. We know this because we've seen its breath, great plumes of water vapor and ice erupting from cracks near its south pole, venting into space like geysers. When NASA's Cassini probe flew through those plumes, it tasted something astonishing. Salts, organics, even hints of hydrogen, a potential food source for microbes. Imagine what might swim in those black oceans. Perhaps nothing more than simple cells clustering around hydrothermal vents on the seafloor, feasting on minerals and heat. Perhaps something stranger, creatures evolved in a world without light, blind but sensitive to currents, glowing softly in the dark. We don't know, but we may soon find out. Missions are planned. NASA's Europa Clipper, ESA's JUICE, and perhaps one day landers that will drill through the ice or sip the vapor from geysers. If they find life, even the simplest microbe, it will change everything. Because if life thrives in those cold oceans, it means biology needs neither sunlight nor mild skies. It means life can bloom in the dark, in isolation, in places we once thought sterile. And if it can happen there, it can happen anywhere. Now think of what that means for our question. If life arose on Europa or Enceladus today, it would not be the first life in the solar system. Earth holds that title, at least as far as we know. But if Earth itself was seeded from another world, if life can leap between planets,
then those moons may not be isolated experiments. They may be part of the same web, cousins in a family that began long ago on some ancient world. And if panspermia works, it may work both ways. Impacts on Earth fling dust into space. Some of that dust may fall on Europa or Enceladus. Perhaps their oceans already hold Earth microbes, dormant or thriving. If so, the solar system is not a scattering of lonely worlds, but a connected system, life moving like pollen on a cosmic wind. But even if life there arose independently, it would still answer the greatest question: is biology inevitable when conditions are right? Two origins in one solar system would shout the answer across the void: yes. And if yes here, then yes everywhere. For now, the oceans keep their secrets. We can only guess what swims in their black depths. But soon, perhaps within our lifetimes, we will send machines to drink from those plumes and tell us what they find. Until then, we look inward, not outward, to ponder what this means for us. If Earth was not the first, if we share our roots with other worlds, what does that say about our place in the cosmos? Are we special? Or are we just one branch on a vast, sprawling tree that stretches from star to star? In the next part, we'll wrestle with that idea, the philosophical shockwave that comes if life is not only common, but connected. If we are not the beginning nor the end, but merely a link in a chain older than Earth itself.
What if Earth wasn't the first? What if life bloomed on Venus, on Mars, or in some hidden ocean long before our planet stirred? What does that mean for us, for the story we tell ourselves about who we are? For centuries, humanity has clung to the idea of uniqueness. First at the center of the universe, then the only world with life, then the sole cradle of intelligence. Each step has humbled us, and each step has widened the horizon. But this would be different. If life began elsewhere before Earth, it would topple the last illusion of centrality. We would no longer be the origin, but a continuation. Our roots would sink not just into Earth's soil, but into the cosmos itself. Would that make us less special or more? On one hand, it would strip away the notion of singularity. We would not be the first flicker of biology in this system, let alone the universe. We would be one of many, a latecomer, an inheritor of a legacy we did not earn. For some, that might feel like loss. But on the other hand, it would bind us to something vast, to a story written across worlds, to a resilience that outlasts planets. If life could begin, perish, leap, and bloom again, then we are part of a lineage more enduring than mountains, older than oceans. That is not smallness, that is wonder. And there is another truth, quieter but profound. If life moves between planets, it is not passive. It does not wait for permission. It seizes every chance. It endures catastrophe, darkness, exile, and survives. That stubbornness is in us. It is why we thrive in deserts, on ice, in orbit. It is why we dream of Mars, of ships, of stars. Perhaps we feel the call of other worlds because deep down we remember. Not in memory, but in matter. If our ancestors came from a different sky, if their home died and their dust crossed the void,
then migration is in our blood. The urge to wander is not cultural, it is chemical. It is written in the code of life itself. And what of meaning? Some argue that if life is common, we are diminished, one voice in a cosmic crowd. But is a flower less beautiful because others bloom? Or is the garden richer for their presence? If biology thrives wherever it can, then the universe is not empty, but alive. And we, thinking, dreaming, questioning, are its consciousness, for now. But here is a paradox. If life is hardy enough to spread, if it leaps from world to world, then why have we found no trace of others beyond Earth? No signals, no monuments, no whispers in the dark. Perhaps the answer is time. The universe is old. Civilizations may rise and fall like tides, rarely overlapping. Or perhaps intelligence is rare, even if life is not. Still, the discovery of a single microbe on Mars, a single cell in Venus's clouds, would shatter the silence. It would tell us we are not an accident, but part of a pattern. It would tell us life belongs not to one world, but to all worlds that can hold it. And then the question would turn inward. If life can wander, can we? Not just with rockets, but as life has always traveled, by persistence, by drift, by seeding new shores. Could we too become more than earthbound? Could our descendants, human or post-human, one day carry life's torch to the stars, as microbes once carried it to us? If Earth was not the first, perhaps it is not the last. Perhaps we are not the origin, but the bridge, between what was and what will be. Between seas long vanished and skies yet unborn. In the next part, we'll look ahead to the future of life and to the possibility that what happened before will happen again, not by accident this time, but by design. Because if life can migrate by chance, imagine what it can do with intent.
One day, Earth will die. That is not prophecy, it is physics. Our sun, steady now, is slowly brightening. In 1 billion years, its heat will boil the oceans. In 5 billion, it will swell into a red giant, scorching the sky. Long before that, asteroid impacts, supervolcanoes, or self-inflicted wounds could bring catastrophe. No world lasts forever. And when Earth's time comes, what then? Does life end here, or does it do what it has always done, endure, adapt, escape? If history is any guide, life does not surrender easily. It clung through asteroid strikes that darkened the skies for years. It survived ice ages that locked the planet in frozen silence. It even weathered the Great Dying when 90% of species vanished. Each time, life bent but did not break. And if it can survive that, why not the death of a world? For microbes, the escape route may come unbidden. An asteroid impact could blast fragments of Earth into space, carrying spores sealed in stone. Some might fall on Mars, on Europa, on Titan, where warmth and water wait beneath ice. Some might drift for millions of years, perhaps finding a new home around another star. The old blind migration, written in rock. But this time, life has more than chance. It has will. It has us. We are life made conscious, life with engines, with rockets, with dreams. Already we have walked on the moon, sent probes to the edge of the solar system, landed rovers on Mars. These are not ends in themselves.
They are rehearsals, because one day, whether in 1,000,000 years or 100, we will need to go. And when we go, we will not go alone. Wherever humans travel, life follows, in our breath, in our blood, in the bacteria clinging to our skin. When we build habitats on Mars, greenhouses on Europa, colonies among the stars, we will carry Earth's genes with us, not just ours, but forests, fields, oceans in miniature. This will not be the first migration, only the first deliberate one. The first time life leaves its world not as a refugee, but as an explorer. A new chapter written by design rather than accident. And perhaps in doing so, we will become what panspermia has always hinted at, a link in an endless chain. Life seeded Earth, Earth seeds the stars, and so on, without end. Worlds bloom, wither, and bloom again, not in isolation, but in a web of connections stretching across time and space. This vision changes everything. It means life is not a prisoner of planets. It is a force, flowing outward like a tide that began long before us, perhaps on Mars, perhaps on Venus, and will roll on long after Earth is dust. But here is a question to trouble the mind. If life leaves Earth, what will it become? On new worlds, under new skies, will it still be us? Or will it diverge, as life always does, into forms unrecognizable? Will our descendants, biological or synthetic, remember their origin? Will they know that they were not the first, that the story they carry began long ago on a different world? Perhaps they will know. Perhaps they will tell that story as they spread from star to star, the story of Venus, of Mars, of Earth, of the leap from ocean to space. And perhaps they will wonder, as we do now, whether someone came before them. Because if life is ancient and restless, if it has moved for billions of years, then maybe we are not the first travelers. Maybe others crossed the void long before us. Maybe even now their dust drifts among the stars, carrying the seeds of worlds we will never see. In the next part, we will ask that question. If life has spread across space for eons, could there be civilizations older than ours? Not just microbes, but minds. And if so, why haven't we found them? If life can leap between worlds, if it can endure in ice and fire and drift across the dark for eons, then we must face an extraordinary possibility. Perhaps we are not the first. Not just the first life, but the first minds. Consider the age of the universe, 13.8 billion years. Our sun is young by cosmic standards. Stars like it have been shining for billions of years before Earth existed, with planets orbiting in their warmth. If biology begins wherever conditions allow, then life could have started on other worlds long before our planet formed. And if life began, why not intelligence? Perhaps other beings have walked their own paths from chemistry to consciousness. Civilizations that rose and fell before the Earth cooled. Civilizations so old that their ruins have crumbled into dust, their stars gone cold. The thought is dizzying. If that's true, where are they? Why is the sky silent? This is the heart of the Fermi paradox, the question that echoes through the corridors of astrophysics. If life is common, why don't we see it? There are answers, and none are comforting. Perhaps intelligence is rare. Life may bloom often, but minds are fragile, a freak of evolution that seldom appears and seldom lasts. Civilizations may flare like sparks and vanish before they can reach the stars. Or perhaps they endure,
but they do not call out. Perhaps they are quiet by choice or by necessity. Silence may be survival in a galaxy where noise draws predators, or perhaps their thoughts run on channels we cannot hear, signals we cannot comprehend. There is another possibility, stranger still, that we have not looked long enough. Radio has been with us for a century, a blink in cosmic time. We have scanned the sky for whispers, but the universe is vast and our search is shallow. A signal could flash for 1,000 years and still miss us entirely. And yet, for all the silence, one truth remains. If life can move between worlds, if Earth was not the first in its own system, then the odds tilt. Life is not fragile, it is fierce. It endures, adapts, spreads. That makes the emergence of minds more likely, not less. Could those minds have left traces? Not signals, not monuments, but biology. Imagine a world where intelligence arose, perished, and scattered its seeds, perhaps not by will, but by accident. Spores blown into space by storms, microbes riding rocks torn free by impacts. Perhaps even here, on Earth, we carry genes that once pulsed in an alien sea. It sounds like myth, but science does not flinch from strangeness. We know life shares genes not just between species, but across kingdoms. Bacteria swap DNA with plants, with animals. Viruses stitch fragments of code into our own. If migration happens on one planet, why not between planets? Why not between stars? If that happened, if we are part of a lineage older than our world, then the story of life is not local, it is galactic. It stretches back through dust and darkness to beginnings we cannot name. We are not the first thinkers, only the latest, and perhaps not the last. But if others came before, what became of them? Did they die in silence? Did they ascend beyond matter, leaving only echoes? Or are they out there still, hidden among the stars, watching the newest voice join the chorus? We do not know. Perhaps we never will. But the possibility should shape how we see ourselves, not as rulers of a lonely world, but as heirs to a legacy written in stardust. And here is the final turn. If we are not the first, if others walked this path, then our future may mirror theirs. Civilizations that endure do not burn their worlds. They do not squander what life gives them. They learn to live with the cosmos, not against it. If we cannot do the same, we will join the silence. In the next part, we will leave the past behind and look forward to the long future of life in the universe. A future where worlds die and stars fade, but life, restless and stubborn, refuses to end. Imagine the far future, not centuries, not millennia, but trillions of years from now. Stars have burned out, galaxies have thinned into whispers, the universe is old and tired, its brilliance dimmed to embers. What becomes of life then? If history tells us anything, it is that life endures. When Earth was molten, it waited. When Earth froze, it clung. When fire rained from the sky, it found shadows and survived. Life does not yield easily. And if it has crossed worlds before, if it has leapt oceans of darkness, then perhaps it will endure even the slow death of stars. How? One answer lies in migration. When a sun dies, life moves outward to new stars, new systems, new homes. We see this pattern in miniature now as life shifts with climate, fleeing deserts, following rain. In the deep future, the scale changes, but the impulse remains. If intelligence persists, the strategy becomes grander. Not spores on meteors, but arcs and engines, ships carving paths through interstellar night. Civilizations may harvest energy from dying suns, build habitats that drift in the void, tether themselves to black holes for power. They may store consciousness in machines or scatter it as code in beams of light. Even without minds, life may continue. Microbes sealed in comets, frozen in ice, might wander for eons, waiting for chance to thaw them. Chemistry does not hurry. It can afford to wait. But even migration has limits. In time, the universe will cool. Stars will gutter out. Galaxies will fade. And the cosmos will slide toward heat death. A silence so deep it erases even memory. Can life fight that? Some dream of cosmic engineering, vast structures to harness the energy of black holes, the last engines in the dark. Others imagine universes beyond this one, bubbles in an infinite foam, and wonder if life could slip between them, seeding new realities when this one dies. These ideas sound like myth, but so did flight once, and fire, and thought itself. The point is not certainty, but possibility. If life has endured this long, through fire and ice and emptiness, who can say where its ambition ends? And here is the thread that binds this to our question. If Earth was not the first, then life is older than our world, older than our sun. It has already crossed gulfs we can barely conceive. We may be the latest vessel, not the first. And if that is true, then the story we write is not a beginning, but a continuation. What role will we play in that story? Will we be a footnote, a species that rose and fell, leaving nothing but fossils? Or will we become a bridge, carrying life forward as microbes once carried it to us? The choice is ours. For the first time, a planet's fate rests in the hands of its own life. We can cling to Earth until it fails, or we can do what life has always done. Move. In the next part, we will come home, to the question that started all this. What if Earth wasn't the first? What does that truth mean for science, for philosophy, for the way we look at the stars? And finally, we will close with a vision of a cosmos alive, a universe that refuses to be silent.
We have traveled far, through time, through science, through speculation. We have walked the boiling plains of ancient Venus, the riverbeds of a young Mars, the frozen seas of Europa. We have traced the paths life might take, drifting on stone, leaping between worlds, crossing the gulf of stars. Now we return to the question that began this journey. What if Earth wasn't the first planet with life in our solar system? What if life began elsewhere, on Mars, on Venus, long before Earth was ready? Imagine it, a blue Venus beneath soft clouds, its shallow seas alive with tiny cells. A wet green Mars, rivers whispering across its plains, microbes stirring in its lakes. Perhaps life bloomed there while Earth still burned beneath a molten sky. For millions of years they thrived in silence, unaware that fate was waiting. Then came the fall. For Venus, the sun's embrace grew too warm. Oceans boiled, clouds thickened, the greenhouse spiral locked. The world became a furnace. For Mars, the heart cooled. The shield died, the air fled. Rivers froze, the sky thinned to nothing. Did life vanish with them, or did it flee? We know rocks leapt from Mars to Earth, hurled by ancient impacts. We know microbes can survive in stone, in vacuum, in darkness. We know Earth, when it finally calmed, was bombarded with debris from other worlds. If even one fragment carried life, then our story began elsewhere. We are children of a lost world,
or of two, or of many. If that is true, what does it mean? For science, it means life is not an earthly accident, but a cosmic pattern. It means the ingredients of biology assemble wherever water and energy dance together. It means habitability is not unique, and neither are we. For philosophy, it means we are older than Earth. Our lineage runs back not 4 billion years, but perhaps 5. It runs not through one world, but through several, in a chain of migrations older than mountains. We are not the first. We will not be the last. And for wonder? For wonder, it means this. When we look at the stars, we are not looking at strangers. We are looking at cousins, at kin, at worlds that may hold echoes of our past or seeds of our future. Perhaps even now, on some icy moon, something stirs, a microbe, a vent dweller, a fragile flame in the dark. Perhaps that life is ours in a way we cannot yet imagine, kin by descent, by accident, by drift. Or perhaps it is alien, utterly, irreducibly other. If so, the universe is deeper still. 2 origins in one solar system would mean life is not just likely, but inevitable. The stars would not be silent gardens, they would be forests, and in those forests perhaps minds grow like fruit, rare but not alone. This is what the question gives us, not certainty, but possibility, a wider sky, a longer story, a story in which we are not the center, but a thread in a tapestry stretching beyond imagination. And here is the final turn of the circle. If life moves between worlds, then what we do matters. We can carry that story forward, or we can let it end with us. The choice is ours, and it begins now in our laboratories, our telescopes, our ships, our dreams. Because if Earth wasn't first, then we are not the beginning. We are the continuation, the bridge, the next step in a journey that began long before we were born and will go on long after we are gone. In the final part, we will close that circle, not with an answer, but with a vision of a universe alive, a cosmos that refuses to be silent, a vision that begins, as all stories do, with a question: what if?
The question was simple. What if Earth wasn't the first planet with life in our solar system? The answer has carried us through molten beginnings and frozen ends, through oceans lost and oceans hidden, through the resilience of biology and the silence of the stars. And now, at the end of this long journey, what remains is not certainty, but wonder. Imagine a universe where life is not an accident, but a rhythm, a pulse that beats wherever conditions allow. Not rare, not fragile, but restless, moving, persisting, refusing to die. Perhaps it began in darkness, long before Earth was born, on a world now shattered or swallowed by a star. Perhaps its seeds drifted through space, riding dust and ice, falling like rain on newborn planets. Perhaps they fell here, on this blue sphere, and woke in its seas. If so, then we are not original. We are continuation. We are what came next. And if life can travel once, it can travel again, across planets, across stars, across time itself. Not in haste, but in patience, a patience measured in billions of years, a patience that turns death into migration, endings into beginnings.
What would that universe look like? Not empty but fertile, not silent but full of whispers, of microbes in alien seas, of forests under red suns, of minds dreaming under strange skies. Some young, some old beyond imagining, some gone, leaving only traces in chemistry, in code, in the dust between stars. And we are one note in that music, one flicker in that vast illumination. But even a flicker can burn bright, even a note can carry the theme. Perhaps one day, when Earth is dust and the sun is cold, something will remember. A being on a distant world, born of a lineage that began here or began elsewhere and passed through us. Perhaps they will speak our name, or something like it, and know we were part of their story. Or perhaps no one will remember. Perhaps memory is as mortal as matter. But even then, the story will go on, not in words, but in life itself, in the chemistry that will not quit, in the spark that leaps from stone to sea, from world to world, from star to star. And that brings us back to the heart of it all. We are not the first, and we will not be the last. That truth does not make us small. It makes us part of something vast, a saga written across the cosmos, a tapestry woven from light and dust and time. So the next time you look up at the night sky, do not see emptiness. See potential. See kinship. See oceans under ice, clouds over crimson plains, worlds waiting for a dawn that may never come, or may already have come and gone, leaving only silence. But silence is not absence. Silence is possibility. And in that possibility lies the greatest truth of all. Life is not a miracle chained to one planet. It is a traveler, a storyteller, a force that takes what it can, gives what it must, and moves ever outward. If Earth wasn't the first, then everything changes. Not just our past, but our future. We are not the origin. We are the bridge. And the road ahead is as wide as the stars. So ask the question again. Whisper it to the dark, to the dust, to the winds between the worlds. What if Earth wasn't the first? And then listen, because one day the answer will come, not in words, but in the hum of engines, the crackle of signals, the heartbeat of life rising again in a place where none should be. Not the first, never the last.